Homogeneous boundary value problems, course code HSC08, presented by Saichen, Computer Science and Engineering, Data Science. Introduction to boundary value problems. A boundary value problem involves a differential equation with conditions specified at the boundaries of the domain, unlike initial value problems, which specify conditions at a single point. In engineering and physics, BVPs model steady-state phenomena such as heat disruption, wave propagation, and structural deformation. A homogeneous BVP has zero boundary conditions and are a homogeneous differential equation simplifying analysis using superposition and eigenfunction expressions. The general form is L of y equal to f of x with y of a equal to y of b equal to 0 for homogeneous conditions where L is linear differential operator. Homogeneous BVPs are foundational in solving partial differential equation via variables, especially in data-driven modeling and mathematical formulation of homogeneous. Consider the second order linear ordinary differential equation y double dash of x plus p of x y dash x plus p of x y of x equal to 0 defined on interval a comma b with homogeneous boundary conditions. Common boundary conditions include y of a equal to 0, y of b equal to 0, y dash of a equal to 0, and y dash of b equal to 0, and Robin mixed linear combinations. The problem is homogeneous if both the differential equation and boundary conditions are homogeneous, leading to linear operator eigenvalue problem. The solution space is a vector space. Non-trivial solutions exist only for specific eigenvalues when the problem is an eigenvalue. Existence and uniqueness depended on the properties of P of x, Q of x, and the boundary conditions gone still. Problems are class of homogeneous BVPs of the form d by dx of P of x d by dx of Q of x equal to 0 with homogeneous boundary conditions. They arise naturally when solving partial differential equations like the heat or wave equation using separation of variables in Cartesian, cylindrical, or spherical coordinates. The eigenvalues are real, discrete, and countable with corresponding eigenfunctions y of x forming an orthogonal set under the weight function r of x. Orthogonality integral of a comma b y of m x y of n x r of x dx equal to 0 for m not equal to n, enabling series expansions of arbitrary functions. Completeness of eigenfunctions allows representation of square integral functions for solving non-homogeneous problems via eigenfunction expansion. This theory overview, eigenproblems and non-trivial solutions. For homogeneous BVP non-trivial solutions, eigenfunctions exist only of specific values of a permanent lambda called eigenvalues. Example y double dash of plus equal to 0 y of 0 y of 0 equal to y of L equal to 0 is eigenvalues lambda of n pi by L square and eigenfunctions y of nx equal to sin n pi x by L where n equal to 1 comma 2 comma 3. Non-trivial solution y of x equal to 0 always exists, but physical relevance requires non-trivial solutions corresponding to resonate or natural nodes. Eigenvalue Each eigenvalue, eigenfunction pair of represents a natural mode of the system, such as vibrational modes in a string or heat modes in a rod. The spectrum of eigenvalues may be finite or infinite depending on boundary domain geometry. Separation of variables in partial differential equations. Homogeneous BVPs emerge naturally when solving linear partial differential equations via separation of variables. Substituting into the partial differential equation separate variables, yielding an ordinary differential equation in space and one in time. The spatial ordinary differential equation becomes Strum problem with homogeneous boundary conditions at x equal to 0 and x equal to L. Solving this yields eigenfunction x of n of x and eigenvalues lambda of n which determine the temporal behavior. The general solution of superposition u of x comma t equal to summation Cnx of nxt nft where coefficients determine in initial conditions. Boundary conditions. Dirichlet boundary condition. Dirichlet boundary conditions specify the value of the solution in boundaries y of equal to 0, y of equal to 0 in the homogeneous case. Applied to y double dash plus lambda of y equal to 0. The yield sign eigenfunctions y of nx equal to sign n pi x by L with lambda n equal to n pi L whole square for n equal to 1, 2, 3. This condition model fixed endpoints such as vibrating string clamped at both ends or zero temperature at boundaries. The eigenfunctions form an orthogonal basis for L square of L, enabling Fourier sine series expansions. In such expansions are used in spectral methods and functional data dimensionality reduction. Newman and Robin boundary conditions. Newman and Robin conditions specify the derivative y dash of equal to 0, y dash of p equal to 0. Modeling insulator of free boundaries in heat flow of mechanics for y double dash plus lambda equal to 0 with Newman conditions. Eigenvalues on lambda equal to n pi by L whole square where for n equal to 0, 1, 2 with eigenfunctions cos of n pi x by L. Robin conditions are linear combinations alpha y plus beta y dash equal to 0 at a boundaries modeling convective heat transfer or impedance conditions. Robin problems yield transcendental equations for eigenvalues tan root of lambda equal to h by root of lambda. By requiring a numerical root finding. These conditions appear in data-driven partial differential equation models, a boundary flux estimation from sensor data. Green functions are homogeneous. Green functions represent the response it takes due to points satisfied with homogeneous boundary conditions. For self-adjoint operators in symmetric reflecting reciprocity in physical systems. The solution to log equal to f of x is y of x equal to integral g of x summation g of summation d summation reducing the PVP to an integral equation. Green's functions are constructed using homogeneous solutions. Finite different method. When you think it ends, it begins and on the spectral methods and eigenfunction expansions. Applications of numerical stability and convergence. Numerical methods in which is must ensure stability. Small coordinations in data do not cause large emission errors. Eigenvalues solvers must handle condition matrices arising from high frequency. Summary and key takeaways of this homogeneous. Thank you.